My name is Denise Aranda, and I'm a Contamination Control Engineer and Planetary Protection Specialist. So space is a very violent environment for materials. We have atomic oxygen that we need to worry about. We have the vacuum. We have thermal cycling. You have a temperature difference that can range from minus 150 degrees Celsius to plus 150 degrees Celsius. So that thermal cycling, along with all the other factors, is really detrimental on materials. And what we do in this lab is we bring these materials and we test them. One of the reasons why we really need to understand contamination control for different projects is twofold. One of them is when you expose spacecrafts and satellites to the very violent atmosphere that is space, you need to understand how those surfaces are going to degrade, and you need to understand how that's going to affect your instrumentation. Then more importantly, when you're exploring other planetary bodies, let's say Curiosity, for example, on the Martian surface, you want to be sure that when you are taking those chemical samples and you're analyzing them, you have the confidence of saying that the organics that you collected on the surface are truly from Mars and not contaminants that were introduced from Earth on its track over to Mars. So you want to make sure that you can isolate those particulates and those species so that you know where they originated from. So outgassing is a phenomenon that occurs in materials. What you see over here is our thermal vacuum chamber, where we test both subsystem, full-scale satellites, and test coupons for outgassing. What ends up happening when materials are exposed to ultra-high vacuum, they start releasing these gas molecules. So here at ambient, we're about 780 torr. When you start getting down to the 10 to the minus 6, 10 to the minus 8 range, which our thermal vacuum chambers do, you start having these releases of gases. The reason why that's important is, one, not only are the materials degrading, which could affect your thermal control surfaces, but these gases can also condense on things like mirrors, solar panels, and that could affect your performance of the overall spacecraft. So what we try to do is identify materials that limit the outgassing and limit the risks to the spacecraft. These are one of our smaller thermal vacuum ovens, and we use these to pre-bake materials before they're integrated to the subassembly, in this case SAGE. So the nice things about these ovens is that they can go down to the 10 to the minus 7 torr, which simulates the vacuum of space, and it's also instrumented with these really detailed and precise instrumentation. So this is what the inside of the oven looks like. One of the things that you can see right away is that we have a platen, and we can actually control it such that the oven would be one temperature, let's say, plus 110, and this platen can go cryogenic. We can go down to minus 20 and even below. So the nice thing about that is that we can simulate spacecrafts when they're in orbit, where one face could be really hot and the other face can be really cold, and we can see how they can react. It's instrumented with thermocouples, and here's where we do our preliminary test for outgassing rates. So we'll put whatever the hardware is in here, we'll close the door, we'll take it to high vacuum, we'll throw heat, and we'll do thermal cycling. As these materials start experiencing the high vacuum and the heat, they start releasing these gases. And that's where this instrumentation comes in. This is called the quartz crystal microbalance. So this is what it looks like. These guys weigh about 25 grams. We actually put them in satellites, and what this gives you is mass deposition rate of contaminants. So you'll see that there's a crystal right there, a quartz crystal. There's also one inside here at the shaft. The way the QCM works is initially both of these crystals are vibrating at 15 megahertz. And once this is placed on the instrument, the gas starts coming off and starts accumulating on this crystal. As it gets heavier, it changes frequency, and the QCM gives us a delta frequency between the exposed surface and the enclosed one, and that'll give us a mass deposition rate. So that'll tell us how quickly these gases are coming off the test article. However, it can't tell us what the species is. So this gives us mass deposition rates, but it doesn't tell us what the species is. The second piece of instrumentation we have is the RGA. It's a residual gas analyzer. What it does is it has an ionizer inside of the vacuum oven, and as these gases are coming off, they come in contact, get ionized, and go through a mass spectrometer. Then it spits out a graph with atomic mass units and partial pressures. So what this allows us to do is being able to see real time what these gaseous species are, and that paired with the QCM will give us mass deposition rate and species of the outgassed materials. I think the biggest challenge that we face is the threat of silicone. Silicone is something that we find very common in electronics. However, when you put it into space, it could be very, very detrimental to instrumentation, specifically for thermal optical surfaces. So we have certain chambers that are used for flight projects that are silicone free. You are not allowed to use any silicone at all. The fear is that when silicone starts outgassing and it starts condensing on a mirror, when it's exposed to UV light, it turns this yellowish brownish color, and now you cannot see through the optical lens. You get all this degradation in your data, and it's really, really difficult to remove. So trying to find things that meet the engineering and electrical needs that do not contain silicone has been a little bit of a challenge for a lot of projects. The rule of thumb has always been, if you can avoid using silicone in any of your materials, please do so, because they can be very detrimental to the performance of an instrument. As contamination control engineers, we span a wide variety of needs. In this lab specifically, we deal with things that are going to low Earth orbit, things that are going into deep space. But within this industry and this very specialized field of engineering, you also have biomedical devices that are also made in clean rooms. Another important one that uses these same types of techniques are microelectronics and chip manufacturing that are also very sensitive to particulate contamination. And we all collaborate and share our lessons learned for different kinds of devices that we use to help mitigate the risk of contamination. If we have certain models, we can try to predict where these molecules are going to condense, and we can design around that so that if the silicone is in the system, we can mitigate the risk and make sure that it doesn't condense on our sensitive surfaces.